So, hello everyone, and welcome to this new instance of our seminar series also of Physics and Machine Learning meets Engineering. My name is Andrea. I'm a former lecturer at the University of Bath, and together with Zach, a postdoc at the Turing Institute, who cannot be with us today, and David, a PhD student at the Turing, we are the organizer of this seminar series at the Turing Institute, which is the National Institute for Data Science and Artificial Intelligence of the UK. Today, we have the pleasure to host our speaker, Mohannad, and who is going to talk about the. Sorry, Mohannad, I cannot see your.
Okay. Oh, you cannot see me?
Yes, I couldn't see the title.
Okay, sorry.
It's going to talk about learning physics guided neural network with competing physics laws. A summary results in solving eigenvalue problems. This particular session will be much more interactive compared to the other times, so please feel free to ask questions during or at the end of the talk. Before starting the presentation, I will kindly ask David to present the speaker for us today. Thank you.
Yeah, thanks, Andrea, and even more thanks, Mo, for joining us today. I will introduce you briefly before the start of your talk. So Mohannad is a doctoral candidate in computer science at Virginia Tech. He has earned a Master's of Engineering degree in Electrical and Computer Engineering at McGill University, and also a Bachelor's of Science degree in Computer Engineering at Jordan University of Science and Technology. He has also gained industry experience as a software engineer at Microsoft for over 6 years. Mohannad's research is interdisciplinary and at the intersection of machine learning and scientific discovery in several domains, such as physics and biology. In his research, he works on bridging the gap between machine learning approaches and human knowledge, an effort that is quintessential for ensuring the machine learning models, which have pervaded all aspects of life, do not violate priors established by experts. Mohannad is also interested in machine learning visualization and explainability and advocates for machine learning models that are more transparent with their decision-making process. Anna, thanks for joining us today, and I shall hand over to you now.
Thank you very much, David and Andrea. Hello, everyone. Thank you for attending my seminar today. Again, my name is Mohannad Elhamod, and I'm presenting today Learning Physics-Guided Neural Networks with Competing Physics Losses. And this work was published March this year, and first authors are me and Jabu, and you actually hosted Jabu like a couple of months ago in your seminar. So this work is a joint work, me and him as first authors. And we're both at Virginia Tech. We have collaborators in Binghamton University and University of Massachusetts. So, okay, so what we're talking about today is, as the interest of this seminar is physics-guided machine learning, which has recently been gaining popularity a lot. It's an alternative to purely data-driven model. So traditionally, we train by measuring error in the data, which is usually a training MSE loss between the true label or the true value and the predicted value. But this can lead to solutions that might violate certain constraints. So for example, I'll give a very simple example. Let's say you're trying to predict the length of some rod, right? You cannot get negative values. So there is some constraint on what the values can be. You can think about it in more complex setting, like what if your answer violates some physics constraint, like the conservation of energy. So not all answers are created equal, and sometimes we have constraints on what the answer can be. So the proposed, so what we want is, in the context of physics, we want our answer to be physically consistent. We want to stay away from physically inconsistent models. So what is the proposed solution? Is to modify the optimization of the objective by adding a physics loss. or I refer to it here as a physics guided loss, PG loss. So the question now is, the crux of this seminar really is, how do we balance the contributions of these losses? Usually or traditionally, there is always like a lambda trade-off coefficient that we put before the losses, and we play with it as a hyperparameter. We try to tune it, and but generally it's held constant across the training process. So that's really the focus of this seminar, is talking about this lambda. So this is even worse when you have multiple physics losses, like you have multiple constraints and you're trying to optimize all of them. And this is especially worse for two reasons. One is you have more hyperparameters to optimize. Second of all, these physics losses can actually compete. And what we mean by compete is that some physics losses might have minima at certain parameter values, local minima, while the other ones might have local minima in different places, or even a global minima in a certain place. So depending on where you like how you balance these loss terms, you might end up in one place of the parameter space rather than the other. Because if you emphasize on this loss with respect to this loss, you will end up in one of these. If you emphasize on physics loss 2 instead of physics loss 1, you will probably end up with a parameter near, like, let's say 0 here, right? So how you set these lambdas affects your parameter space and affects the solution you will get. So what we are advocating in our speech is that these lambdas cannot be really held constant. They have to be adaptively tuned, and we will talk more about that in later slides. So the use case, or the use case we address here is solving eigenvalue problems, and generally in the two cases I will talk about, we're interested in finding the highest or lowest eigenvalue solution, and that's usually of interest in many physics problems. And the reason we pick this kind of problem is that, first of all, it's interesting from the physics point of view. Second of all, numerically solving eigenvalue problems is known to be expensive when you have for large matrices, let's say. And we think that, yes, training neural networks can be also expensive, but once you train a neural network, then you can do inferences or predictions on the fly, like very fast. There's very little computations involved there. So we think, like, even if we take a constant large amount of time to train these networks to solve an eigenvalue problem, once we train it, when we're done with that, which is a constant cost, then the inference will be much faster than rerunning a numerical method every time for a different matrix. So what I mean here is, given an A, a matrix A, we want to find the eigenvectors Y. As I said, we're interested in a particular eigenvector, usually largest or smallest. And of course, once you find Y, you can find the eigenvalue. So that's in a nutshell what we're doing. So the case study one, I'll start with this one, and then I'll move to the second one after we analyze this. Case study one is an n-spin Ising problem. I'm not a physicist, so I'm going to give a very superficial explanation of this. I'm sure you guys know more than me about this, but basically it's a Schrodinger equation of the form as an eigenvalue problem, where we have like a magnetic field perpendicular to the spins of multiple particles, of n particles, and we can characterize this system by a Hamiltonian matrix. And this can be like, this Schrodinger equation can be solved as an eigenvalue problem, where the eigenvectors are the wave functions. They are the eigenvectors of the Hamiltonian, and the eigenvalue would be the state energy. And here, so solving this would give if we want the ground state energy, we would be aiming for the eigenvector vector with the lowest energy, the lowest eigenvalue. Yeah, so this is the problem in general. And the primary objective here is to maximize the cosine similarity between predicted spectrum and target spectrum. So when I'm talking about the spectrum, it's the wave function. And the reason we pick cosine similarity specifically and not like MSE is that generally speaking, MSE is bad for a high dimensional space. Cosine similarity is considered a better measure. And second of all, we are really interested in the profile of this wave function rather than the absolute values. So we want to get the profile. We want to get we don't care about the exact value. We just care about the shape of the profile of the wave function. So that's why we chose the cosine similarity as the objective for the loss function in this case. So just in a nutshell, what the system looks like. This is what a regular neural network looks like. We have matrix A. We input it into its neural network. We get the predicted eigenvalue and eigenvector for an A from DTR. And what I mean by DTR is the data set, the training data set. Okay. And I know it says mean square error here, but you can use cosine similarity or mean square error. We use the mean square error for the training, but we use the cosine similarity for assessing the quality of the prediction. So the cosine similarity is used in the testing data, really. But for the training, we still use the mean squared error. And we do gradient descent on that. So that's a neural network, a purely data-driven neural network. Now, if we add physics-guided loss, we can use A from the training data, but also note that we can use an A from an unlabeled data set. So usually training data is labeled, right? We have the A and we have the corresponding Y's and B's, right? But for the PG loss, which I'll talk about in a bit, we don't really need the Y's and B's. We only need the A. And that's what we call unlabeled data because we don't have the label, we don't have the Y's and B's, we only have the A's. And the A's are enough for calculating the PG loss. So doing that is really helpful because now we don't really need a lot of label data because as we know, the label data needs to be calculated, which means you need a numerical method to calculate those training samples, right? And that's already expensive. That's what we're trying to solve, right? So the less data we can use, the better, right? Whereas generating the A's, which are the unlabeled data, if we just want to generate an A without the Y's and B's, that's a lot less computationally expensive. So we can generate a lot of DU, a lot of unlabeled data to help us with the physics-guided loss, even if the training data is looking. Okay. All right, so what are the PG losses here, the physics-guided losses? We have two losses. We call them the spectrum loss and the characteristic loss, okay? And I'll explain what those are in a bit. So the characteristic loss is if we have an input A and a prediction Y and B, then the constraint we're saying is whatever answer you get, Y and B, they should satisfy the Schrodinger equation, okay? So this means AY minus BY should be 0. Okay, that's our constraint, right? And the way we do that is simply putting the Schrodinger equation, the magnitude of Schrodinger equation, the subtraction of both sides of the Schrodinger equation. That should, if the answer is right, that should be 0. So minimizing the magnitude of that should be as small as possible, which is 0, right? And here we just normalize by Y, because it's just easier for the neural network to optimize when we normalize. So that's the characteristics loss. We want whatever Y and B we get, whatever Y hat, B hat, which are the predictions that we get, we want them to satisfy the Schrodinger equation. Now the PG loss 2 is the spectrum loss. And the spectrum loss is basically, we want to minimize B, right? So we want the C loss to be 0. We want it to satisfy the characteristics, the Schrodinger equation. But we know the Schrodinger equation has multiple solutions, right? There are multiple eigenvectors and eigenvalue pairs that will solve it, right? But like I said in the beginning, we want the ground state energy, the minimum eigenvalue. So we want to minimize B, okay? And the way we do that is we put it in an exponential form, and minimizing this would minimize B, okay? So that's the S loss. And so the combination of both is minimizing the S loss leads to selection of the lowest eigenvalue, right? It's a valid solution that is minimal. That's the combination of both at the same time. All right. So we already talked about this. So the key issue here is the PG losses can compete with each other during gradient descent, leading to poor local minima, right? So like I said, C loss, the characteristics loss, which is the Schrodinger equation satisfied, has multiple solutions, multiple minima, right? But if we add the S loss and the S loss gravitates the parameters towards the solution with the lowest lambda, right? Then optimizing the order of optimizing these two losses can lead to different solutions, right? So if we optimize the C loss first, we might end up in this local minima, right? And then we're stuck there. So these losses can compete with each other. Their dynamics together might or might not lead to the best solution. Okay, so that's the problem we're facing. That's the problem we want to address. So how do we address that? By dynamically tuning the coefficients of these losses, by emphasizing on one loss at a certain phase and then emphasizing on the other loss at a certain phase. So we call that annealing and cold start. So we start with an annealing S loss, and we cold start C loss. And by that, I mean, we set the S loss, we set the coefficient of the S loss high and the coefficient of the C loss low or almost 0. And this way, the total physics loss would be mostly S loss. So we're gravitating towards this solution, right? We're gravitating towards this region. And then gradually we switch. We start emphasizing more on the C loss and less on the S loss, right? So if we do that, then after we are at this region, then the C loss can do its gradient descent in this region. And then we are more guaranteed to gravitate towards X0, which is the right solution. So this order is important. If we have started with C loss and went to this region, it might be very hard to get back to this region where the actual generalizable solution is. Okay, so that's the crux of our method here. So to show some results, just to show the evaluation setup in this baseline models. So like I said, we have the mean squared error, the data loss, the pure data loss is we apply the mean squared error on the training data, which is which is much smaller in size than the unlabeled data. But for the physics losses, since if we go back here to the physics losses, you can see none of them use the true labels. They all just use the predictions and A, right? So we don't need labels for these. We only need the A and the prediction, right? Whereas the data loss, if we go back here, the data loss takes the mean square error between the prediction and the true label. So we need the true label for the data, for the pure data loss, right? But physics losses, we don't need the labels, which means the S loss and C loss can be trained on the unlabeled data. So we have a lot more data available now for them. Okay, we might only have, I'm just throwing numbers here. We might have a couple of 100 training data points, but maybe thousands of unlabeled data. So let's see how that does. And the way we did it, we wanted to test the generalizability, the extrapolation ability of this model. So we trained it only the training data, or the data, the label data, which uses the mean squared error, only sees data from Bx less than 0.5, which is ferromagnetic material, like system, let's say. And the unlabeled data has both. Okay, so the data the system is seeing, the labeled data the system is seeing, is only ferromagnetic, but we are going to test it on both ferromagnetic and paramagnetic. We know in machine learning that if a model doesn't sees data only from a certain regime, it will only be able to predict well and interpolate in that regime. It's not going to be able to extrapolate. That's a well-known thing about neural networks. So by adding this physics laws on the unlabeled data, can we do better than that? So let's see. So here are the results. NN means a neural network without any physics losses. It's just a black box. And CoPhy-PGNN is our method. And we have like an ablation model where we have CoPhy-PGNN, but we only show it the training data. We don't show it the unlabeled data. Okay, so we do the adaptive coefficients of cold start and annealing, but we don't show it unlabeled data. And you can see here that the training data is only in this phase here. But all models do very well. The cosine similarity is 1. All models are doing really well. Once you start going into the paramagnetic phase here, you can see that both the black box neural network and the one that only uses the training data start really doing much worse, right? Whereas the CoPhy-PGNN that used the unlabeled data does very well. Okay, it stays around 1. So we can see like using this unlabeled data really helps with the physics losses, really helps with extrapolating beyond the area where you had labeled data. Another thing that we can look at is something that has become more trendy lately, which is visualizing the landscape of neural networks. This is something that has gained momentum in the last, especially in the last couple of years, I would say. So looking at the landscape helps you see if the neural network generalizes well or not. So if we look at the black box neural network, we can see that it has, this is the training MSE, the test MSE, and then the physics loss. We can see the train MSE is pretty low. So that's good. It can predict the training data. It fit the training data very well. The test MSE is a little higher, so it's doing well, but we can see this is not really a minima. Like here in the training data, you can see this is, the model is in a minima in the parameter space. So this is like a cross section in the parameter space. We know the parameter space is very large. We take a cross section in it, a random cross section, and there are many papers about why is this useful or valid. We might think like, oh, taking just a 2D cross section in such a high parameter high dimensional parameter space is meaningless. But there has been a lot of papers that say like it will tell it is a good qualitative measure of how well your model is. But I'm not going to go into that. This is not the subject of this seminar. But in a nutshell, the training MSA is, the model is pretty good. It's in a minima. It's in a low MSE value minima, so that's good. The test MSE, not really in a minima. It's a little higher than the training MSE, and the PG loss is pretty high. It's in a minima, but not the best minima. Okay. But if we look at CoPhy-PGNN, we can see that across the board for all the losses, we are in a minima and in a low loss value compared to the black box. So that means actually our method did improve the results. It has a low physics loss. It has a low error on the test data. So across the board, it's better than a black box. So those are the results for the first case study. The second case study is we try to apply the same method on electromagnetic propagation. So I'm going to describe the problem very quickly. We take 10 periodically stratified layers of equal length of mediums with certain refractive indices. So the refractive index n can be any number from 1, 2, 3, 4. Okay, so only 4 possible values of the refractive index of each layer. Okay, and epsilon, the permittivity, is equal to n squared. Okay, and again, I'm not a physicist, so I'm not going to go into the physics details a lot, but we can spatially profile this the electromagnetic field of this system. So by a Schrodinger, sorry, not a Schrodinger equation, like an eigenvalue problem. So the input A would be describing the structure and the permittivity epsilon, and KZM is the propagation constant along the layers, and the HM would be the coefficients of the Fourier transform of the electromagnetic problem. And here we're interested in the largest eigenvalue, not the smallest one. So we have to modify the losses a little bit to get the largest instead of the smallest. But it's still described as an eigenvalue problem. The setup here is a little different. So the matrix A is a complex valued matrix and which shows the system to be a size of 401 by 401 values, which is significantly larger than the one we used for the quantum physics problem. And we only have a couple of hundred training data points. But the thing is here, we choose n equals 1 for the first layer. So if we go here, I said each layer can have one of these possible n's, but the first layer, we keep n equals to 1 all the time. Okay. So why do we do that? Because we want to train the system on a regime where n is always equal to 1 in the first layer, but we're going to test on all the possible values. And we're going to see if the model is able to extrapolate. Okay, so again, extrapolation is a key goal in our problem. So if we look at the results, we can see that for n equals to 1 in the first layer, CoPhy-PGNN does better than the others, but they all have a relatively low relative eigenequation error. And by relative eigenequation error, I mean, I'm just going to write it here. I should have written it on the slide, but I forgot. Okay, so that's what I mean by the relative eigenequation error. It's like how far is the eigenequation, the subtraction of the both sides of the eigenequation, how far is it from 0? So the closer to 0, the better, right? Because that means, oh, we satisfy the eigenequation, right? And we just divide to make it relative, divide by the right side. So we can see like here, CoPhy-PGNN is better across the board, but as we move to a permittivity that is different from 1 in the first layer, we can see that black box gets worse, and also a PGNN analog, and by PGNN analog, I mean constant lambdas. If we just use constant lambda, it also gets worse. So that means to us that, first of all, using unlabeled data helps. Second of all, adaptive tuning also helps. Okay, because this is without the physics losses. This is without adaptive tuning, right? So using both of them gets us a relative error that is close to 0, no matter what the permittivity of the first layer is. Okay, which means it extrapolates very well. Moving on to the second result. So here, I will try to talk about the shortcomings of our results. So these are the results of comparing the different solvers that the top 3 are neural networks. The bottom 3 are just numerical eigensolvers. And I'm gonna compare the execution time, the relative eigenequation error, and the overlapping integral. And just FYI, the overlap integral, you can think about it as the cosine similarity in the complex valued vectors. But just think about it as cosine similarity. It's just what we use when we have complex values. So there are 3 things we can notice. First of all, the numerical solvers have a much better relative eigenvalue error and overlap integral. So we can see here the overlap integral for numerical solvers is like close to 1, close to perfect. And the eigenequation error is like in the order of 10 minus 7 minus 10. It's very low. Okay. Whereas for the numerical solvers, the error is much, much higher. Overlap integral is in the order of 0.6, not too impressive. Okay. So we acknowledge that we're nowhere close to getting something that is close to the numerical solvers, at least for this challenging problem, because we chose an A that is large relatively, 400 by 400, complex value. So it's really 800 by 800, right? So we have to admit that, okay? But taking that into account, we can still see that CoPhy-PGNN does better than the other neural networks. It has a higher overlap integral and a lower relative eigenequation error than the others. So that means in the context of neural networks, we have improved the results. But the other thing that I also want to bring is that the execution time, the average runtime. So this is the average runtime over the entire test set, which we said is about 1,300 examples. For each example, on average, the neural network takes something in the order of 10 to minus 4 seconds, whereas the numerical solvers take something to order of 10 minus 1, let's say, okay? So this is just to re-emphasize what we talked about in the beginning, is that, yes, the neural networks are nowhere close yet to solving as well as the numerical solvers. And maybe that's because we need more hyperparameter tuning, more higher computational power, so we can, again, run bigger models, run more hyperparameters. So we have proven a concept, but making this actually compete with numerical solvers will take a lot more than just a small research lab in our university, right? So, but to our point is that we can see that our solver is like at least 1,000 times faster. Okay, so if we can get this to work at the level of the numerical solver, we can see the benefit. It's a lot faster. That's the point we tried to emphasize. And the other thing we want to emphasize, also another shortcoming, is that if we plot the histogram of the overlap integrals over the test set, we can see that CoPhy-PGNN usually gets an overlap integral equals to 1, much more than the other neural networks, which is great. We always want an overlap integral close to 1. But also it seems we sometimes get an overlap integral close to 0, okay? And this is because our interpretation of that is that even though we always get like a valid solution, we don't always get the desired solution. And by that I mean, that means the solutions that correspond to an overlap integral of 0, they are valid eigenvectors, but they are not the largest eigenvector. Okay, and that's why the overlap integral is 0. Okay, so that means, again, in this challenging system, in case study 2, the electromagnetic propagation, yes, we're doing better than the other neural networks, but there's still work to be done. This is a future improvement we need to do. And like I said, I would put my bet on more resources for larger models with more hyperparameter tuning. But at least we've proven the concept in the quantum physics problem, in the Ising model problem. Now we tried to do this on a larger model to see the results, and these are the shortcomings that we can see. So that's a room for future improvement. So just closing remarks. The things I want you to come out with from this talk is adaptive tuning of multiple loss terms is necessary to reach a global minima. We have seen that the neural networks that did not use the adaptive tuning, we did not do that well. And also that PG losses can help extrapolate beyond scene data. We've seen that's a very important result from our work. When we did not use the PG losses, yeah, the other neural networks were doing well in the regime where it has seen similar training data. But once we have shown it data outside that regime, it didn't do as well. So PG loss really helps with extrapolation. And finally, scalability issue. As I said now, our model did not scale as well when we chose a larger problem. So that's something we need to work on. So that's my work in a nutshell. And I would like to acknowledge NSF for the grant for this work. And before closing, one last slide I want to show, which I would love for the audience to help me with that. Because it seems you also have a lot of experience with physics, with problems of combining physics into neural networks. So I have been very interested in this problem generally, of the problem of how to balance different loss terms. This problem is not, strictly speaking, a physics-guided neural network problem. It appears in multitask learning and many problems in neural networks. So this is not specific to physics, but I'm sure if you have used physics-guided neural networks before, you have struggled with fine-tuning these coefficients of these loss terms. So I wanna ask if the audience would like to share their experience with this and how they address it usually. I tried to do some literature review on it. I don't feel the community of machine learning has addressed this sufficiently so far. They always seem to do something ad hoc or some heuristic with no proper justification of how they chose the lambda values or how they chose their method to do the lambda values. In our work, we showed a way, like we showed how we needed cold starting and annealing, right? We're not saying this method will work for every single physics-guided neural network or for every single multitask learning. We're just saying in this context of the eigenvalue problems, it worked. We're not prescribing it to every single problem. But I would like to know if you guys have some experience with this and how do you choose your balancing loss terms? I've seen the community, usually 90% of them, they just say it's a hyperparameter, we fine tune it, it's just a constant. I've seen some people try to balance the magnitudes of the loss terms. I've tried to see some papers try to balance the gradients of the different loss terms. And finally, I've also seen people treat the lambda itself as a parameter that is updated using gradient descent. These are the ways I've seen the community deal with it. I don't think any of these has a very strong, solid foundation. I don't think enough research has been done on this, but I would love to hear your thoughts on it and if you had experience and what you think. But that's my talk. Thank you.
Oh, thank you, Mo. So thanks for talking. It was very interesting. So I'm not a particularly expert in this, so I will refer if there is anyone in the audience who would like to contribute. Maybe meanwhile, I can ask you a question on your talk if that's okay.
Yeah, sure. Go ahead.
So I don't understand very well how do you include unlabeled data in your algorithm. So for unlabeled data, I assume you mean like a eigenvalue eigenvector pair.
So let me repeat. Usually in neural in training neural networks or machine learning in general, you need labeled data. What we mean by labeled data is that this is your neural network, right? You have an input, let's call it A, and you have an output, let's call it X, just for
For instance, in the case of the Ising ferromagnet, for labeled data, I mean, what do you mean by the label? Is it like ferromagnetic and paramagnetic state?
No, just simply put, what we mean by labeled data is if you have both the X and the Y. So in our case, if we have A, which is the input, and we have the Y and the B, which are the output, this is called labeled data. If we only have the A and we don't have these, that's called unlabeled data. Basically, we have a system with no solution.
Okay, sounds good.
So it's easy to create a lot of systems, right? Just hypothetically, without solving them. You can just create a problem, but not solve it.
Oh, okay. Well, I'm afraid that we don't have many contribution from the audience of this. But there is a question from someone in the chat.
Okay. Not sure if you. Oh, you can read it. Go ahead.
So there is a person in the chat saying, I'm not sure if you might have read this paper, but you might have some useful info when and why beam fails to train. Okay, and then there is a link for you.
Right. Go ahead, Carlos.
Oh, sorry. No, just something that I'm first year PhD student, so like don't really know what I'm doing, but I've been looking at this one precisely because of like similar problems. In this paper, they talk more about the mismatch between basically the minimization of the loss of the boundary term versus the interior of the domain when working with physics-informed neural networks. And they have an interesting perspective using the neural tangent kernel to kind of like calculate why one term converges faster than the other, and actually a kind of like useful way to tune those. Say, I don't know how much they will be applicable in this case, where it's like two physics term laws that are not necessarily the same. It's not necessarily the same laws applied into, let's say, subdomains of your problem, but they're two different losses. So I don't know how much it can apply, but I think it might be useful, this kind of perspective, like calculating the eigenvalues of the kernels of each one of the losses, and that kind of like giving you an idea of how to weight them so that like one of the losses doesn't overpower the other one.
Right. I'm not gonna say I'm an expert on the tangent kernel perspectives. I've brushed over it, I would say. It didn't occur to me to look at it from this perspective, but I thank you for bringing it up. I'll try to go back to it and see if I can learn from it in our context. But I also I feel a lot, and this is I'm not saying this is not my comment on their paper or anything. It's just my comment on the field generally. In machine learning, whenever there's some theoretical work, they make a lot of assumptions which might not really hold. And when you actually train your average neural network. So I feel a lot of these theory papers, even though they're valuable for sure, I'm not sure how much they actually apply to training your average neural network. I don't know what your thoughts on that are, Carlos, but this is my thought too. It's a challenge.
No, I do agree to a certain extent. Like obviously here, even just the assumption of like the infinite width limit is a pretty big assumption.
Right.
I think the interesting part is that it seems that things converge towards a limit. Some of the properties, like for example, the variation in the eigenvalues, and so I haven't yet used it myself. Like I'm actually working on a kind of like toy problem and trying to apply this perspective. So I don't really know if it works for like a small or like very deep narrow neural networks, but I think maybe at least it contains some kind of useful information calculating this kind of kernels, or at least the change in the eigenvalues of these kernels. So maybe it doesn't allow you to, let's say, do a kind of like zero shot guess at putting these setting these hyperparameters, but I do wonder if they can kind of be interleaved the same as we do validation loss, doing some kind of, let's say, gradient check every time and see how these eigenvalues are varying, and use that to kind of like change the weights of the losses. But again, just mostly just like thinking here, haven't really got anything solid to put my money behind.
No, I hear you. I don't think, I mean, I wish someone comes up with a solid way to do it, but that's not like you or me. Like I think the field in general hasn't addressed this adequately yet. But again, I'm not saying that as a criticism per se. It is a hard problem. I'm not saying it's an easy problem. Why hasn't no one done it? I'm just saying it's hard, but I think it needs more attention. That's really what I'm saying.
Yeah, I do agree with that. It's pretty interesting as well.
Okay, so are there more comments or questions from the audience?
Yeah, if I may step in. Mo, thank you very much for this talk. I actually, well, my own experience in balancing loss terms is, as you said, it's like, I'm glad to hear it's 90% of the community does the same. So it's basically on trial and error effectively. So it's not really exciting, but that's my own experience on it. I did try once also trying to use the Lagrange multipliers as learning parameters, no? But no, I didn't quite manage to make it work. But effectively, the problem obviously is that you need to be very careful, no? How do you apply those as learning parameters? Because they will just try to minimize the loss error. They will just try to make them as low as possible, no, or as negative as possible. So it's not trivial to introduce them as learning parameters. Having said that, I did in January I saw a work from someone who has actually been a host here, like a couple of months ago, who presented a work in the IAA SciTech forum in January, but I was trying to find the paper, and I cannot, for some reason, I cannot find it. But it will again be on the class of trying to use the Lagrange multiplier as the lambda as a training parameter. That's it, really. That's all I know about it. I'm afraid.
No, thank you for sharing that. I really, sorry, I just want to say, like, the reason I posed the question is, sometimes you feel like you're trying to tackle a problem, and you read the literature review and it's like, oh, I can't find anything. But then a couple of minutes later, like, you meet someone, it's like, oh, did you read this paper, right? Yeah, so I was hoping, like, by posing this question, maybe there is something I haven't learned about or known about yet, and maybe someone from the audience has, so I can learn from them. That's really why I asked the question.
Yeah, I will definitely find the paper and try to send it to you. Just for some reason I cannot find it now.
Yeah, sure.
If I had known beforehand, I would have searched for it.
It's okay.
Earlier. But it was not it was only a single lambda parameter, but it should be the same problem still.
Right.
I meant to ask something about your method, though.
Sure.
You said that the order is important, isn't it? So obviously, because you had you were able to probably visualize the behavior of each physics function. You were able to choose in what order to tune up and tune down the lambdas. But so what would, in the case it was not possible to, or it's not clear what order to go on, then what could be done?
Okay, yeah, that's a very good question.
Yeah.
And I think my answer is I don't know, because again, I'm not trying to oversell our work. Like I said, this prescription we said, like about cold starting and annealing, it worked really well for the eigenvalue problem. But again, I'm not trying to recommend it like, okay, use the exact method for any physics guided loss and you will get it. No, I'm just saying, if you know that the different losses one has multiple minima, the other doesn't, and
that's what I meant
you can reason that minimizing one before the other makes sense, then yes, please go ahead and use this. But if there is no clear order, I honestly don't have a magic bullet.
Yeah, because in your case, you have one that is monotonically increasing, no? So you have one minima in one of the functions. So, but if in the situation where you don't have that, or you will have on both equations different minima, then it's not so trivial, isn't it?
No, it is not trivial. Yeah, I don't want to oversell the prescription. Yeah, it's definitely not that trivial.
Yeah, okay.
Okay, so if there are no more comments or questions, I think we can thank our speaker again. So thank you, Mo, for being our guest. And yeah, we'll see all in a couple of weeks for the next seminar.
Yeah, thank you very much for hosting me. This was a lot of fun. Thank you very much.
Our pleasure.
Thanks.
Have a wonderful day.
Bye, everyone.
Thank you, everyone, for joining, and thanks, Mo, for your talk.
Thank you very much. Have a good day.
Bye-bye.
Thanks.